So we're going to recall that if G is a P group, and we say that G is acting on some set X, I've gotten really consistently good at doing those thingies. Anyways, then, what do we know? The size of X is equal to the size of the fixed points, the things in X which are fixed by all elements of G. So this is equivalent to this mod P. You can or you can choose not to put parentheses around this mod P. It doesn't seem to be a really big deal. Anyways, so let H be a group of size P squared, and H is going to act on itself by conjugation. Well, then what is H to the H? This is just by definition, this is all elements H and H, which are fixed. Well, here, let me be consistent with how I wrote this in my notes. This is a collection of all elements X of H, such that HX H inverse is equal to X for all H in H. Because this is H acting on X under this under this group action, and then this holds for all H and H. But look, if you multiply on the right here, this is the set of all X and X, such that HX equals XH for all H and H. But what is that? That is just by definition the center of H. Okay? So then, let's see here. So P squared, remember, this is the order of H. But then this is equivalent to the size of H to the H, which is equal to size of Z, center of H. And this is all mod P, i.e. this congruence here is mod P. So P squared is congruent to the center of H, the size of the center of H, mod P. All right. So we know that the center of H is not empty because, well, the identity is in there. So the fact that Z of H, the size of Z of H is equivalent to P squared mod P. Well, P squared is equivalent to 0 mod P, so this has to be equivalent to 0 mod P, which means that, let's see here, what are the options? Either the center of H is going to have size P, or the center of H is has size P squared. So assume for contradiction, I'm just going to write AFC. I like to do that because assume for contradiction is 3 words, and that has a lot of letters. And this is 1 word with 3 letters. So anyways, so we're going to assume for contradiction that is P. Okay. Well, the center of H is, it's like stronger than being a normal subgroup, because a normal subgroup would just mean that, oh, HX, H inverse is contained in H. But this is actually equal to what you started with, which in particular is in H, rather than this conjugation giving you possibly another element in H. And that's all you need for normality. So anyways, so Z of H is a normal subgroup, and therefore we have this Z of H goes to 1 is a short exact sequence. We know that we get a short exact sequence like this anytime we have a normal subgroup. Okay, and where do we go from here? Let's see here. then the size of h mod z of h, well, the size of h is p squared, and we're assuming here that the size of the center of h is p, and so this is p. And so, let's see here, we have the center of h and h mod the center of h are both isomorphic to z mod pz. And that's because there's only one group of size p, and that's z mod pz, the cyclic group generated by an element of size p. And I don't know if we've proven that, but that's not a difficult thing to prove. It's something that you definitely cover in like a more introductory course in algebra, whereas here we're just sort of flying by a few of the more basic facts. So this is more of a basic fact that for any prime, if you have a subgroup of prime order, then it's just the cyclic group generated by an element of whose order is that prime. So, anyways, so the center of h and h mod the center of h both have size p, and thus are isomorphic to this. Now recall that, now I guess this is recalling for me because I've seen the homework exercise that this comes from. Here, let me write it down. If there is a subgroup H that's subgroup H of G such that H is contained in the center of G, and G mod H is cyclic, then here I'm going to put primes by these just so that we don't confuse them with the groups that we're considering in this problem already. So, and this is cyclic, then G prime is abelian. And that's actually not too difficult to prove, but it is a really useful fact. So, let's see here, it was not assigned as a homework problem, but it was in one of the homework problem sets as like a optional exercise. And so that's not one of the ones I'm going to upload in my exercise. Well, it's not one that I have to upload in that exercise set, but I might anyways, just because it's such a useful fact. But I invite you to try to solve this on your own if you can, to prove this on your own if you can. And if not, then just try to look it up somewhere. So G prime is abelian. Thus, okay, so the center of H is contained in the center of H, and H mod the center of H is Z mod PZ, which is cyclic. And therefore, H must be abelian, right? Thus, H is abelian. So then the center of H, well, the center of H is just all of H because H is abelian. So this is H just P squared, which is a contradiction. Now, when you see this contradiction proof, you might think, oh, well, we concluded that, since we concluded that the size of the center of H is equal to P squared, you might think that, oh, maybe you didn't have to assume for contradiction that this was true. Maybe you could have just started with having the center of Z, the center of H, and just going from there and proving that the center of H must have size P squared. But we really did have to assume for contradiction that this is equal to P, because this argument really relies on that fact, because it relies on the fact that H mod Z of H is isomorphic to Z mod PZ, and you might be able to prove this even when you don't know, even without assuming this. But I didn't take the time to think of it, and it's certainly not obvious to me. So I think that it's hard to kind of take it. It's generally a good rule of thumb if you have a proof by contradiction that could be just a direct proof, then the direct proof is generally going to be a much nicer, cleaner proof. I don't think that this is one of those scenarios. So anyways, we have a contradiction. Thus, the center of Z must be P squared, because we assume for contradiction that it's P. We got a contradiction. Therefore, the only other scenario is this one, which is where the center of Z is P squared. So then the center of H, the center of H is P squared. So then the center of H equals H, and hence H is abelian. Okay. So here's a quick corollary. If H is a P group, then the center of H is not trivial. It's not just the identity element. And let's see here. How would you prove what? I feel like this is a very obvious corollary, but let me just make sure I have all this straight. Okay, so a group of order P squared is abelian. Oh wait, so if we just look at this proof, if we look not at the result, but if we look at this proof, then if we consider this, if we have a group of order P to the n instead of P squared, then if we get to this step, we see that P to the n is equivalent to the size of the center of H mod P. And right, if it were the case that the center were trivial, then you'd have 1 mod P is equivalent to P to the n, but P to the n is going to be equivalent to 0 mod P, and so that's impossible. And so, therefore, yeah, it is trivial, because, well, I guess the thing is, I don't think it's so much a corollary of this theorem, it's more a corollary of this particular technique that was used in this theorem. Because if what you have to do is you have to use the same group action, but consider a different group, and you basically just stop after this point, more or less. After this point, you're pretty much almost completely done. So yeah, that's how you would prove this corollary. And so this is one of the theorems that we're going to use in discussing finite groups.